right. Good morning again, everyone. So we are going to try to do things a little differently. There's a part of the course where we're going to do things a little differently here. So if you brought your laptop, I see plenty of you have already the laptop up on the table, up and running, perfect. If you brought your laptop, bring it up. Okay, we're going to use it. If you don't have a laptop, bring up your phone. What we are going to need is an Excel document. Okay, Excel, LibreOffice, whatever you are using. Okay. So prep that up while we get warmed up, and I'm going to show you how we're going to use it in a few minutes. All right. So where are we at? Still module 2. We are going to finish module 2 today. So I'm going to already tell you that right now so that I don't have to rush it at the end of the session. I'm going to upload the PDF of the slides. At the end of the PDF of the slides is going to be a list of practice exercise. Okay. So even if we don't reach, if I don't have time to scroll through them for you during the lecture, I don't really have anything to say about them. They are just practice exercise, right? So you know where to find them. I just wanted to be clear at the beginning that you will have some extra slides at the end with some practice exercise. What we're going to do today is, last time we talked about translating back and forth between Java and English, okay? And we said that one of our focus in this class will be, as a first step, to give you an algorithm in plain English, a pseudocode, and have you translate it into Java, okay? So that's what you can expect for IE02. And then at the very beginning, I mentioned that tracing skills. So this is what we are going to focus on today. Today, we are going to just talk about that one skill, code tracing. And I'm going to try to highlight how it's different than just reading code. So here's an example that's actually, it's doing the job. It's not a perfect example, okay, but it's a piece of code that generally does the job well to convey the meaning of this is not translating code, this is understanding code. Take a look. What do we have here? So how do you look at that already? Structure, right? So tell me about this code. What do we have going on here at a structural level? Yeah. Sentinel control? Kinda. It's a weird one, right? So we definitely have a loop here, okay? Inside the loop, we have an if statement. Now the interesting part, is it a sentinel control loop? Is it a counter control loop? Is it a whatever control loop? It's a little weird, right? It uses n. So maybe that's a counter. Let's see. I compare n to a value. Do I increment or decrement n? Whoa, this is a little weird. I don't increment or decrement n at the end of the loop, but inside the loop, no matter which part of the if will execute, I'm doing something that's going to result in incrementing n or decrementing n. But this time I divide to decrement it, I multiply to increment it. So it's kind of, so far it looks still like a counter control loop, okay? But it's kind of a little bit different than from what we have seen so far. Okay, I can take that, I can stomach that. And then the n is read from the user here. So hold on a minute. Didn't I say something about, Sentinel control loop, you read data from the user? Yeah, but that's data every iteration, right? Every spin of the loop, you read data from the user. Here, that's not what we are doing. So I can rule out Sentinel control loop here because I'm reading one value before the loop starts, and that's going to tell me pretty much how many times I'm going to spin. So what else? Declaration of variables here, a scanner, some prompt to the user followed immediately by reading a value from the user, followed immediately by some aesthetic BS, okay, like skip a line and stuff like that. That loop, we know it's a kind of counter control loop that's going to be a little weird. Every iteration I increment result by 1, so result is going to be equal to the number of iteration of my loop, because every time I go through it, I increment by 1. And then if flag is 0, flag is an int, okay, it starts at 0. If flag is 0, set flag to 1. Okay, weird. And then divide n by 3, and then go to the next iteration. So now if flag is not 0, so it's 1, for example, set it to 0. Okay, so we toggle, okay, and then multiply n by 2. With all that being said, let's see if I can remember what number I had. Yeah. With all that being said, if I type, when I'm prompted to enter a value for n, if I type the number 12, okay, what is going to be the number of iteration that this code goes through? Of all the time where I prompt you to answer, if somebody was answering actually correctly to that one, I don't know what I would do, okay? Because it's, what's the problem here? It's not trivial. It's not like the building blocks, that we had in module 1, where I have a counter control loop. It starts at 5, it goes 5, 4, 3, 2, 1. If I input 12 here, okay, it's going to say 12 is greater than 0. Okay, result is equal result plus 1. So result is going to be 1. Flag equals 0, that's true. Flag equal 1, okay, I take note of that. N equal n divided by 3. So my 12 is divided by 3, integer division. That gives me a 4. So now n is 4. N went from 12 to 4. And then next iteration, it's either I'm going to divide again by 3, integer division, so it will go down to 1, or I'm going to multiply by 2, it's going to go to 8. So n is going to go 12, 4, 8, and then whatever values. That's not as trivial to anticipate, okay? We could probably still mathematically analyze that as a series, okay? But it's going to take more work. That's the point. And this is not even a complicated piece of code, okay? That's the idea here. This code fits on one page, on one slide, okay? Most of it is declaration and reading one value from the user, not that bad. And then there's one loop to understand. And one loop with only one if statement inside of it can already cause us, to pause and say, well, I cannot just tell you right now like this what the output is going to be. I need to think about it. So thinking about it in this case is going to be tracing. What I did with you so far, I translated the code pretty much. I looked at the structure of the code. I told you this part does this part does that. Did that help us? Well, it's part of the job, yeah. But when it came time to say, what is the output of this program when I enter 12? What is the behavior of this code when this and this happens? Well, I fell short. Okay, that translation of the code was not enough. So if I run this, well, that's one way to know what the code is going to do, right? To run it. So if I run this, I enter 12, I get a 7. So I have the translation of the code. I see what the code does when I enter 12. That doesn't mean that I still understand the code, okay? I haven't built in my head a sort of model of what is going on here, what is the logic, okay? What are we trying to compute here? So to do that, there's no shortcut, unfortunately. You cannot just stare at the code. Let me phrase that differently. Sometimes you're going to be able to stare at a piece of code, and you're going to say, this is a multiplication table that's being displayed on the screen, or this is a factorial being computed, or this is that. Why? Why do people do this? How do they do this? Actually, not why. I don't know why they do it, but how do they do this? Well, most of the time it's because we have seen that code in one form or the other before. So after I've seen, I don't know, like 255 students write a piece of code that computes the multiplication table, I'm becoming pretty good at spotting a multiplication table code, when I see one. But that's just like routine, getting used to things. But what if I look at a piece of code that I've never seen before? That's a lot more rare, okay? It's really rare to have people able to stare at code like that and just figure it out, in a few seconds, etc., if they have never seen it before. So we need, instead of just that hopeful thinking, I'm going to be able to figure it out if I stare at it hard and long enough, we need some sort of method. So what would Boromir do in this case? He would trace code. So tracing code, there are different ways to trace code. We can trace code by hand. That's why I ask you to prep up like an Excel document on your phone or on your laptop. I'm going to show you how to do it. You're going to do it with me a few times. We're going to do it together, okay? And that's why I'm going to do it during the class, because I want to make sure that you do it at least once, because this is kind of boring, okay? I'm not going to lie to you. This is kind of boring. This is tedious, but that's the only way to be sure. So you'd be surprised how many students, lose points during quizzes and exam because they look at a piece of code and they say, I can do it. I can understand what this code is doing without tracing. I don't need to trace. And then they get it wrong, like 70% of the time, right? And then those of you who are going to actually put in the effort and go through the trace, well, among those, hopefully 90% of you will get it right. And then 10% of you will do the trace, but you'll be thinking about something else, not concentrated enough. You're going to get it wrong, okay? So we're going to actually learn to do it the right way today in class. And then what about those two other methods? Good old println and jgrasp debugger, or any debugger for that matter. Well, these are the things that you are going to use when you are taking an intermediary exam or you are taking the final exam, okay? When you are taking an exam and you have 2 hours on the clock and you need to get that program to work and you realize it's not working, it's not spitting out the correct result, you need to debug, okay? Part of debugging is tracing through the code, making sure that you really understand what you wrote, because obviously you thought what you wrote was going to do this, and when it runs, it does something different. So you need to reconcile, right? Understand what you wrote that is differently interpreted by the computer, tracing. But when you do that under that kind of scenario, a timed exam, you're not going to have time to do it by hand the way that I'm going to show you here. The way we do, the reason for which we do it by hand is to train your brain so that eventually you don't need, this whole table, etc. You become better and better at understanding code without help. But when you are actually in a tight spot, we have tools to help you reliably trace through code. But again, you use those tools, you look at the trace that's generated automatically for you. If you have not trained your brain to think step by step sequentially through a code and pay attention to all the details, that data is wasted on you. Okay, I've seen it's not uncommon. I've seen a lot of students, have a problem with a piece of code and they go through the debugger. So the debugger allows you, for those of you who never encountered a debugger, it allows you to run your code one step at a time, one statement at a time, and it shows you in the code where you are. I'm executing this line. Next, I'm executing this line. Next, I'm executing this line. So it allows you to very slowly go step by step. And for every step, you are going to see exactly what the computer has done so far. What are the values of all the variables in memory so far? How do they change when I execute that next step? So it's an invaluable tool. But if you have a problem with your code and you say, okay, I run my code, it's wrong. All right, I'm going to run my code with a debugger. Slow, 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 slow. It's still wrong. Yes, it's not going to change. The debugger is not going to fix your code, right? It's not going to change how the code behaves. It's just going to give you an opportunity to have the machine help you understand where it breaks. Guess what? If you do the trace by hand just for a few weeks with me, at the beginning of this class, then you'll be able to use your debugger much more effectively. So let's jump in. Here's a piece of code, same code, okay? Here's the same code. This is what we're going to call a trace table. They are going to roughly always have the same format. That's why I want you to have like an Excel document, or if you don't have, a piece of paper will do. It doesn't matter, okay? Whatever you have is fine. I want several columns for this program. The first column is going to always be the line number. So as I execute my program, I'm going to write, for example, the first line I execute is 6. I put a 6 here. And this row is going to represent what happens in my computer after I'm done completely executing line number 6, okay? Each of the column here is going to correspond to one variable. Why? Because I want to keep track of the values inside all of my variables. Remember what I told you like 1 or 2 lectures ago? Like if I trace a program that has one variable, I can use my hand. Okay, as long as it goes up to 5, I'm okay. Then I can use like 2 hands. If it goes up to 10, then I'm getting in trouble. I need to keep track of the value of all the variables in a program when I try to understand what it does. And the more variables there are, the less likely I am to do it just in my head. Okay, so I need a piece of paper. That's all. n, variable flag, variable result, variable scanner, but scanners, generally, we're not going to really pay too much attention to them because we create and initialize them, and then we keep just calling method on them, right? So we don't really change their value. I put it in the table just, out of habit, but really you could even skip that column. But n flag results, yes, they're going to change. And I want to track how they change, okay? And then the last column will be always note. Note is where I try to just scribble down some stuff to make my trace table actually readable. For example, every time I'm going to come here, I'm going to say when I execute line 15, so I'm going to put a 15 here on the line number. I'm going to say, okay, I need to figure out if n is greater than 0. So in the not columns, I'm going to say, is n greater than 0? And then I'm going to use whatever value of n has right now and compare that number and say true or false. And that will allow me to see in my trace table as it grows and grows and grows that this is where I started the next iteration. Okay? So let's do the first one together. Line 6. How do I use those columns? These ones here? Well, when I am done executing line number 6, so that's going to be my first one here, the only thing that changed in memory is n was assigned a 0. So whatever variable gets a new value, whatever variable changes or just get created and initialized, you keep track of the value here. So at any point in time, if I execute another line, another line, another line that don't change n, when I reach this line here, if for some reason I need to, for example, compare n to 0, I'm going to look at the column n and look at the last value the most recent value that I changed. That's going to be the current value of n. Make sense? No question about this? You guys visualize how this thing is going to look like? All right, so let's get cracking. Let's take that piece of code as an example. We are going to put, I'm going to put like a lot this time, then we'll put less, okay? But we're going to put 5 minutes on, yeah, there we go. I'm going to put the counter right here. That's the best spot. We're going to put 5 minutes on the clock. And what I would like you to do is do the trace table, okay? So this structure, whatever you want, wherever you want, piece of paper, etc., and run through that code. Do for me your first formal by hand trace of a piece of code, all right? With the full information. And I'm going to be like walking around. If you just came in or you were listening to me, but you're like, what do I have to do right now? Just raise your hand. I'll come and I'll re-explain to you, okay? But I want to make sure everybody gets this done at least once thoroughly. So let's go. 5 minutes. That should be okay. What number are you starting with? So that's a good question. On line 12, it's going to ask you for a number. We use 12 as an example, so please use 12 as well. Very good question, okay? So when I execute line number 12 here, okay, I'm going to write line number 12 is getting executed. The value of n is assigned a new int read from the user. I'm going to use the value that I used in my previous slide, 12. What's up? Yes, I can. But if I move it, then it's going to hide something else. So the timer is not that important. Let me like get it out of the screen as much as I can here. There we go. It's all the it's always all the variables, okay, plus a column for nuts. All right. Did you just come in a little late? Okay, do you understand what I'm trying to ask you to do here? Or? Yeah. So. Yeah, I want to have like a detailed log, pretty much, of everything this program is doing, and we do it like old school with a table like this. So piece of paper, Excel document on your phone, Excel document on your laptop, whatever you're comfortable with, or even Word document is fine. Yeah, it's a step-by-step, what's happening, what line am I executing? So the first column tells you the line number. So I start at line number 6. Then I go to line number 7, and I go to line 8. So it looks like I'm reading the code, right? But then I get in the loop. So the loop is going to, spin around. Yeah, there we go.
So we start at line 6.
Say that again?
So we start with line 6.
Yes, we start with line 6. Just because I skipped, like the class definitions, the main definition, stuff like that. Not funny, not interesting for the trace. Yeah. Yeah. So what we are doing is I give you a piece of code, okay? And we're practicing doing a trace of the code. So I give you a table format. And what we're going to do is we're going to use that table to say, okay, what is the first line that the code runs? Line 6. So for each row like that, you are going to show me which variable is modified in memory as a result of executing line 6. So line 6 declares int n equals 0. So n is getting a 0 on line 6. Okay, and then I'm going to move to what is the next line that gets executed? 7. And then I'm going to look at, do I change any value of any variable? Do I create any new variable? So I'm keeping track of all the values of all the variables in memory in that table. And I go line per line, I simulate what the code is going to do. So when I get into a loop, I'm going to do this, right? So I'm going to go back, for example, from line 25 is the end of the loop. Yeah, I'm going to at some point jump back to line 15. Okay, but I keep track on that. I stay on that. I try to simulate pretty much what the computer will do. Okay.
So you do each line, don't you?
Yes.
Oh, I was going to say.
And the thing that I'm trying to kind of like sneak in the explanation here is that I don't do each line only once, right? It's like if I was reading the code, I would say this is 20 line of code, 20 line of trace. No, you guys are going to have much more than that, because when you get caught in a loop, you go like line 15, blah, 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 blah. When you reach 35, boom, you go back to 15, okay? So the trace is not the same as translating the code. That's what I'm trying to emphasize here, yeah? Yeah, what's up?
So how would the flag value change if it was like not putting 0?
So when you execute line, what is it, 7, right? Flag is going to get a 0. Mm-hmm. So line 7, you put 0 on your table. And then you execute 8, 9, 10, etc. Next time you change flag is going to be line 18, for example. Mm-hmm. When you do line 18, in the column for flag, you just write 1 instead of 0. So you have a 0 before, and now you see that there's a 1 now. So for any column, if I look from the bottom, I find the most recent value like from the bottom. Does that make sense? Okay, yeah. Once you guys get used to that format, it's a little weird maybe the first time, but trust me, you're going to get used to it, and then it makes sense. Huh? What do you mean? Which variable? That one is not going to get to 0. If you assume that the user entered a 12 here, okay, it should stop. The program should stop when we reach 7. We know that because we ran it before, right? But I think what you're experiencing right now is actually a good thing to experience right now. It's the trace, how it can actually mislead you, and we're going to talk about that like in a minute, okay? You didn't do any, well, you must have skipped a beat or something like that, but that's exactly what happened when we trace. So don't worry, we're going to talk more about that. I'm sorry, you're going to have to repeat that. Go ahead. Yeah, you input the value. So when I execute this line here, when I write, this is line 12 executing, I'm going to put a 12 inside of n, okay? So let's take a look at it together, okay? You guys are all started, you all started the trace table. I think you have a good sense of where this is going. What's the first thing that you notice probably? It takes a lot of time, right? 5 minutes was not enough to get to the end of it. How many of you actually enjoyed the 5 minutes of tracing that you went through? Cool, awesome. So you guys are normal, okay? This is really good. All right, this is not enjoyable. We just have to do it, okay? And that's your number one problem, I would say. I can tell you, if a quiz asks you, for example, what is the output of this code, if you don't immediately figure it out like that because you've seen that kind of code before, you have to trace. Now, most people, when they have to trace a piece of code, either they're not going to do it. I see that every semester, okay? So really stubborn, like, no, I can't figure it out without tracing. Tracing is too boring, I don't want to do it, right? Most likely you're going to not be able to predict what the code is doing if it's non-trivial, okay? Or I'm going to trace, all right, I'm going to trace, but you know what? Physically I'm tracing, but mentally I'm doing something else. And you are going to skip a bit. Why? Because tracing is boring. Why is it so boring? Because we are trying to do what a computer does. Are humans good at repetitive tasks where you have to really be careful, and if you deviate a little bit, on the thousandth time that you repeat something, you are going to cause a wreck? No, hell no, we're not good at that. Computers are good for that. So the whole problem here is not intellectual. You all know how to trace. I can make sure that I sit with you, we'll run through a trace, but you are going to be distracted, you are going to be bored. Be mindful of that. Okay, these are your enemies. Okay, so let's go and okay, everything wants to update on my computer today. Sorry about that. All right, let's go and take a look at the trace. So I'm going to build the table step by step here with you. So we said we start at line 6 just because I cut off, the main declaration, the class declaration and stuff like that. So I write down when line 6 is executed, here's what happens in memory. What happens in memory is n is created, n gets a 0. I write a 0 in that cell of my table. Easy. What about the next line? Well, building block 0, right? Sequential execution of a bunch of statements, one after the other, in the order they are written. So after line 6, I go to line 7. No big surprise there. A variable flag comes to existence and is assigned a 0. We are good. Line 8 is going to be the next line to be executed. Again, sequential execution, and result get a 0. So if I wonder, right here, after executing line 8, what is the value of n? What is the current value of n? I look at the n column. I see no change, no change. The last change I had was a 0. This is the current value of n. The first value that I encounter by going upward is going to be the current value. Okay. All right. And we keep going. So what comes after 8? 10, of course. Why not 9? Because 9 has nothing on it. I'm not going to trace empty lines, right? I'm not that decided to make a long trace table. So I'm jumping to 10, create a scanner. I'm writing special. You don't even have to track scanners when you do trace tables, because really the scanner has a value in it, but it's a special value. It's called a reference. We'll talk more about that in COP2513. Yeah. You could, if you are more comfortable doing it, you could say, here there is a 0. I'm going to write it here because it's still 0. Write it here because it's still 0. Write it here because it's still 0. In the grand scheme of things, it doesn't matter. Whatever you're comfortable with. My advice is don't do that. Just for the reason that when I look at the table like this, if I ask myself, when is the last time that I changed, for example, n? Okay, I can figure this out. The last time I changed n was on line 6. But if I have zeros here and here, it's possible that n didn't change, or it's possible that somehow I reassigned a 0 to it, right? So if you do a spare matrix like that, okay, sparse matrix, not a spare matrix. Anyway, a sparse matrix like that, it allows you to pinpoint exactly when is the last time this variable was assigned a new value. So it can come in handy sometime when you're looking for bugs, okay? What comes after 10? 11. So 11, display, so I went to the next slide. So because I went to the next slide, I recapped here, what is the current value of every variable. But you don't have to do that on your table because you keep scrolling down, right? So now I'm going to go to line 11. And this one is special. It's special because it doesn't change any value of any variable in memory. All it does is display a message on the screen. Let's just say ... And I'm going to put in my notes, ... is displayed on the screen. Why does that matter? Just because when I look at my trace, it's going to tell me, it's going to allow me to easily spot when in my code execution, the prompt was displayed for the user. Okay, so when things happen as a screen, generally I just take a quick note here that this and this happened as a screen on the screen. Okay, same thing for the line 12. I should take a note that says we read a value from the user. Okay, and then the important part is when line 12 is done executing, what happened to the variables? So I should really have written here, hey, I read a value from the user. I'm going to assume the user type 12. A quick note like that, okay? And then I assign 12 to n. That's the result of executing this whole line, okay? What comes after 12? 13. So again, a blank line on the screen. This is what I use my not colon for. Yeah. What about line 12? Sorry. Because we assign it. We assign to n the result of reading, from our scanner what the user typed. So when you trace like that, when you simulate the execution of a code in your mind, if there is input coming from the user, you need to decide what the input will be. So I'm using the same number that I used in the previous slides, when we're just running the code. We said, okay, what happened when the user entered 12? Well, I'm trying to figure out what happened when the user entered 12. So I'm going to assume the user entered 12, but it's an assumption. Okay, it's not like coming from any hard rule. Yeah, absolutely. The question is still the original question that was there a few slides ago. And the question was, take a look at this code. What will happen if the user types 12? So we are still trying to work this out, right? So line 13, display a blank line. 14, there's no 14. 15, okay. This is a Boolean expression that I have to evaluate. Again, different people can do it differently. What I like to do is I write down the Boolean expression that I need to evaluate, and I substitute, for example, n, I substitute n by its value. If I have an expression like n plus 5 greater than 0, I compute the result of n plus 5. I show my work, right? So that I don't miss a bit, miss a skip a bit, miss a step. And then I have here, for example, 12 greater than 0, okay? And then 12 greater than 0 is true. So I write this down. This condition is true. Therefore, none of the variable is modified in memory, but I go to the next line. That's what loops do, right? So I use what I know about the building blocks and how they work, and I use it repetitively. Line 16, result equal result plus 1, okay? Variable assignment, building block 1. So every time I have a building block 1 like that, one of the variable is going to get a new result, a new value. So this is what the variable contains right now. The last time it was assigned was when I was on the previous slide, and it was assigned a 0, okay? And I keep going like that. 17. 17 is an if statement. So you've seen how I trace through a loop. How do I trace through an if statement? Same thing. I have a condition. I need to evaluate it. Flag equals 0. What is the current value of flag? The last time I changed flag, it was set to 0. So flag equals 0 is true. So I'm executing what? This part. If it was false, I would execute the else part, okay? That's how if statement works. So now I'm going to jump from line 17 to line 18. But if my condition would have been false, the next line I was executing was, of course, line 21, okay? I follow the logic. We call that the control flow of execution of a program, right? I follow the logic of the building blocks. So line 18, flag equal 1. Sure, why not? Line 19, n is equal to n divided by 3. So watch out. In programming, we don't care only about values. We care about values and their data type. So n is an int. N currently is 12, okay? 12 divided by 3, 12 is an int, 3 is an int, that's 4 as an int. That's why I put a 4 here. This is what I end up assigning to n. And then what? Well, the if statement is there to choose one block or the other. So the next line I execute is going to be line 25. That is me going from here to the end of my if, okay, statement, if else. And then there's a blank line. 25 is the end of the loop. What happens when you reach the end of the loop? You rewind, okay? So now I'm going to go back to line 15 on the next slide, okay? So let's move. So this is where we are at, okay? N is 4, flag is 1, result is 1. I just copied that from the previous slide, okay? And now I'm jumping from line 25 to line 15. And I test again. What is the current value of N? 4. 4 greater than 0? True. All right. Then next line that gets executed, 16, I increment result. So this is where the trace doesn't have to be purely mechanical. Okay, I've been a robot so far. I've been just doing what a computer would do. That's the goal. I need to be as close to what the computer would do than I can. Otherwise, it's not a trace. It's just, fantasy, right? So yes, I'm trying to simulate what the computer is doing. I'm trying to act like a robot. But here's what's happening. I'm getting bored. So the good thing about getting bored is that when you get bored, generally your brain kicks in and tries to find shortcuts to get you out of the boring situation. For example, this is the second time that I execute result equal result plus 1. When you trace, what I want you to do is keep an eye out for opportunities to understand. Here, I've gone through the entire body of the loop. I never modify result. This is the only place where I modify result in my loop. Every iteration I increment it by 1. Guess what? I'm making an hypothesis now. I'm saying, you know what? Result, this is a dumb variable. It's just going to be a counter that's going to tell me exactly how many times I've been spinning through the loop. That's just my hypothesis for now. So it was 1, okay? And now I come into the loop for the second time, it switches to 2. I'm going to keep an eye on this variable. That makes it a little less boring when you're trying to understand what is the meaning of the code, okay? And you do that as you go through the steps mechanically. So you both play the robot with half of your brain, and then the other half of your brain looks at what the first half is doing and try to figure out, smarter stuff to say about the code constantly as you trace. Line 17, what is the current value of flag? 1. Is 1 equals 0 true? No, it's false. So I go from 17 to 20, the else. And the else has nothing really to do, so I go to 21, and 21 sets flag to 0, and then multiplies n by 2. N was 4, now n is 8. What's going on with flag? Yeah? Yeah, we are toggling, right? Flag is 0. If flag equals 0, flag equals 1. Next spin of the loop, flag equals 1, flag equals 0. Next spin of the loop, flag equals 0, flag equals 1, right? Again, this is what you have to do. Tracing is not just about being a robot. It's a big part of it. It's a part that's boring and where we fail, because we don't pay attention. And we have to be really careful about that. But it's also trying to see patterns. That's what the human brain is really good at, pattern recognition, right? So I've seen this change already 2 times. There has to be a rule here. What's going on? What about this one? It goes 0, 1. Now, can I look at the code? Yeah, it looks like it's always flipping back and forth. Now I look at the code and I understand it, right? So now in my head, result is incrementing by 1 at every iteration. Flag is flipping from 0 to 1 at every iteration. And I'm not going to use that to jump to conclusion. I'm just going to keep an eye out as I do the trace, as I continue doing the trace like a good robot. I'm going to keep an eye out to get more observation, more data to confirm my hypothesis. Right now, these are just my hypothesis about what the code is doing. I need to validate them. Good science, right? So I keep collecting data to validate my hypothesis. Line 22, 23, there's nothing. I should not even have written it. Line 25, I write here end of iteration number 2, just to keep my trace, easy to read if I need to reason about it. And then what's going to happen next slide? I'm going to loop back to line 15. So this is what I have in my variable right now, 8, 0, and 2, okay? And then line 15, is 8 greater than 0 true? So result is 3, yeah, that sounds like I nailed it. This thing is just counting how many times I'm iterating through the loop. Okay, so that's good, that makes sense now. Line 17, guess what? Yes, I'm going to flip again to the first part of the if. Last time I executed this time I'm executing that. That toggles flag. Flag was 0, is going to be 1. Next time around, it will be back to 0, then back to 1, then back to 0. Okay, so I get the idea here. And then n equal n divided by 3. So n is 8 divided by 3, integer division, that's 2. So what have I gathered so far? This thing is weird. This thing keeps spinning, tells me how many times I spun in the loop by keeping track of it in a counter variable here. And then one time it's going to divide n by 3, and the next iteration is going to multiply by 2. So I have a value of n, I divide by 3, it gets smaller. Next time I multiply by 2, it gets bigger. Next time I divide by 3, it gets smaller. Next time I multiply by 2, it gets bigger. So there is a possibility that this thing would never end. Okay, so now I'm looking at it and I'm saying there is something, here going on. If I keep dividing by 3 and multiplying by 2, maybe I can try to analyze it, more mathematically than algorithmically, and I can try to extrapolate what's going to happen. What's going to happen if every time, I divide by 3, then multiply by 2, divide by 3, multiply by 2? Well, mathematically, it's like multiplying by 2/3. So we are going to decrease progressively, okay? So there is a sense, I'm getting a sense now that, okay, maybe this is not an infinite loop after all. Maybe it's just going to decrease. And I need that because I'm already on iteration number 2. I'm getting bored and I don't even know if what I'm doing is going to actually give me any points on my exam, right? So I'm panicking. I'm spending already 10 minutes on this. I don't even know where it's going. So I need to understand, to reassure myself, okay, it looks like we are converging here somehow. And then I keep doing the robot thing. 23, 25, okay, end of the if statement, end of the loop, rewind back to 15. So this is iteration, I lost track, 4 probably. Yep, there we go. Iteration number 4 because results keeps track of that for me. And then the condition is false. So execute the code in the else, flag equals 0, n equal n times 2. So n was down to 2, now it's 4. So we still go down, but we have those hiccups where we multiply by 2 every other iteration, then keep going. Again, 4 greater than 0, yes, this is a 5th iteration. 0 equals 0 is true, so I'm going to set flag to 1. I'm going to divide 4 by 3, that's going to give me 1. I'm almost there, okay? My condition is while n is greater than 0, I almost broke the threshold. I'm at 1. Next iteration, maybe I will stop. No, wait a minute. No, next iteration, I'm going to go back up. Okay, so I know what to anticipate now. I'm not just tracing, I'm not just following, I'm also using my brain to verify my hypothesis, project, and constantly look at the data and what it tells me, okay? So there we go, next iteration number 6. It's so exciting right now, right? So condition, flagged back to 0. Everything makes sense so far. I could write that even without looking at the code at this point. N multiplied by 2. Yeah, go back up. Okay, but I anticipated that. I knew it was coming. And then reach the end. Next iteration. 2 greater than 0. True. Iteration 7. 0 equals 0. Yes. Toggle the flag variable. There we go. Now I divide n by 3. That gives me 0 because it's an integer division. Exactly, yeah. I finally can go home. Please let it be done. And then I reach the end of the loop. And then my condition is false. So when the condition of a loop is false, you remember the building block? That means we go to the next thing after the loop. So I jump here to line 26. 26 is a blank line. So get me out of this loop, please. And then line 27 is going to display the value of result. What is the value of result? 7. So what is this code doing? This code is pretty much, over the course of 2 consecutive iterations, is pretty much taking whatever number I gave initially and multiplying it by 2/3. Okay, the first iteration, it divides by 3. The second iteration, we multiply by 2. But globally, we are multiplying by 2/3, every 2 iterations. And we keep going down. And this program is going to tell me how many iterations it took for me to reach a value that is below 1, an integer value that is below 1. Again, if somebody would have told me that, just looking at the code, I don't even know. And that's never happened, okay? In that case, it's either I uploaded the slide and I forgot about it and you guys saw the slide before to come, or you are that good, okay? But if you are that good, then yeah, that part of the course is going to be really boring for you, right? But bottom line is that for most people, there is no way out. You have to do the trace, okay? So You guys started doing that trace, okay? How many of you completed the full trace? I saw nobody had time in 5 minutes, first trace you do to complete it. Some of you went pretty far, actually. I was impressed. But you know what? This is the first time. Yeah, I didn't expect any of you really to complete. How many of you got the part that you did 100% right? You did? You did. 3, 4, 5, 6, 7. 7 out of how many? I'm really good, really bad at doing that. We're like maybe, I don't know, 40 in the classroom right now. So maybe a fourth. So what's happening? Okay, does anybody think that the trace, for a college level class, what I just showed you is arcana, right? It's like unreachable. I can never develop that skill. Anybody feels like that? No, of course not. It's trivial, right? So again, think about it. What could possibly go wrong while you trace? You understand the building block, you understand how to trace, you go through the steps, you do your best, and then you come up with a result of 9, 8, or you come up with a result that say, my trace is 25 pages now. It doesn't look like it's going to stop anytime soon. I am physically stuck in an infinite loop. Thank you for that. What happens anytime you get it wrong? We get distracted. That's why I do my traces with a slide, because I'm a cheater, right? When I was a student, I loved when a prof would trace a piece of code that was not obvious for us, and he or she would get messed up in the middle, and it's just, that happens, even, if you have been doing that for years and years and years. So you have to arm yourself, be ready for fighting off distraction, and doing it mechanically on a piece of paper like that. Yeah, it's boring, but that's the only way we're going to get through that, okay? Now, here's the danger. Here's the dark side, right? How many of you started building a mental model of what the code is doing? Well, here's the thing. I hope every one of you started. Like I told you, you are going to get bored. Use those juicy brains of yours and try to escape boredom by actually understanding the code and making theories and using those theories to predict. That's science. Okay, theories that allow you to predict results of action before they happen. That's good old-fashioned science 101. So yes, I want you to do that. What's the catch? Don't do it too fast. Okay? If you do trace, so keep your eyes out if it works. I don't care about that. Generally, it doesn't work. But if you do your traces, okay, humor me for like the next few weeks as you work through traces, do it the boring way. Okay, wax on, wax off. I know it's boring. Please humor me. Okay, why? Because as you do that, what you are doing to your brain is you are forcing your brain to look at there's no code, but to look at a piece of code, right? To look at a building block and predict what the building block does. And I know, because I see that in office hours, that even those of you who are very confident that you understood the building block, once in a while I can catch you off guard. Okay, I'll ask you, what is this line doing? And you hesitate, or you have to think like for like 30 seconds, 1 minute, or maybe you get it wrong, right? So yes, that's going to happen. The only way to prevent it from happening is to drill through it. Okay, the same way that nobody wants to do a push-up. But if you, and the last person you want to listen to for advice is on exercise, of course, but letting that on the side, nobody wants to do a push-up, it's boring, but you have a goal here, right? You're training your muscles. Here you're training your brain. Do that for just a few weeks, and I guarantee you that you will be a much stronger programmer. All right, so don't fall on the keyboard, right? Don't fall asleep, fight it off, stay awake, stay with me, do the trace. So I already went over the benefits, okay? You are going to pretty much wire your brain to execute very efficiently each of the building blocks. And more important than efficiently, very reliably. Now, once you get to the point where your brain looks at a line of code and can fill the trace table, without almost thinking about it, when you get really good at doing that correctly and reliably, forget about fast. Do it right, and then fast will come, okay? What you did is you build intuition as well. Okay, so you're going to build intuitions about how the code is working. And then very soon, very fast, by the end of the semester, I guarantee you, you are going to start tracing so much faster. You're going to start, taking shortcuts because you have good hypotheses, etc. And then sometimes you're going to get shortcuts and you're going to hit a wall. But that's okay. Then you have to just slow down and say, okay, I went too fast, do the trace, stupid like a robot, and get it right, and then now I can speed up, okay? But that's how you're going to get better at this. If you try to jump directly to the, I put my hand on the code and I feel this is a factorial, you are going to hit some serious walls, and that's going to discourage you from learning to program. Because if every time you try to do something, you hit a wall, it's not really fun, is it? You don't want to do it like a lot, so you don't want to practice. If you don't practice, you don't get better. All right, so when you download the slides, you're going to notice that the table, the animation that reveal one line at a time, it's gone. Too late. You didn't take picture, did you? No, kidding. So the point is, you need to redo it. Okay, so practice exercise, go back over the previous example, finish it up. Okay, and make sure you get it right. If you don't get it right, that's okay. That's you learning how to do a trace. All right, what about this? I'm keeping an eye on the clock here because, yeah, that took a little longer than I thought. So what about this here? We have something that is a counter control loop. Start value is 0, end value is 5. So I gave names to the variable. That makes me really understand that the end value is what I look out for. N is my counter. The start value means that N is going to be assigned to the start value. Okay, so it's kind of like a well-written counter control loop, easy to understand. Okay, display N at every iteration. So display N a space, N a space, N a space. So all the numbers are going to go on the same line, and then increment N by 1. So yeah, definitely counter control loop. And then display after the loop N is the value of N. So this thing is going to run, display, the counter. So 0, 1, 2, 3, 4, 5, and then tells me at the end of the loop, N is, how much is it going to be? 5? You guys okay with 5? Oh, okay, let's take a look. All right, and it's 5. Got it. So that's what's going to happen when I run it. Again, as you need more practice to get used to the trace table, do the trace table for that guy here, okay? We're not going to do it in class because otherwise I'm going to have to take 2 sessions to go through this, okay? But I want you to practice in between the session. This is a good way to practice the trace table. That will help you for the PQ and the GQ, okay? So the end result, I display my thing, loop from N equals start value to N equal N value. So a loop from 0 to 5 with N lesser than 5 being my condition here, display 0, 1, 2, 3, 4, and after the loop, N is 5. Again, I trace. I act like a robot. I make sure that I mimic correctly what the computer does. And then I get lazy and I try to get smart, okay? So I say, okay, I get it. When you have a counter control loop that starts at 0 and 5, right? There's going to be 1, 2, 3, 4, 5 iterations in the loop. So the number of iterations is going to be the end value, 5, minus the start value. These are just hypotheses, right? But that's how I understand the programs at another level. So I'm making my hypothesis here, and then I say after the loop end, N will be the whatever value I add for N value, for 5. But that's because I have a +1 here. That's because I have a lesser than here. And of course, that should be true no matter what values I have for start value and end value, okay? That part here should be plug and play. But the rest depends on this operator and this value here. You increment, decrement by 1, by 2, by 3. So let's play a little with those moving parts of my code, okay? Let's experiment. And I uploaded this piece of code on Canvas, so you can download it and experiment, run it, change, all those things, see how it goes, okay? I really encourage you to do that as well. What if I change a lesser than by lesser equal? Again, do the trace, okay? Do the trace, take a look at it, figure out what's going to happen. And then you can pick at the slide. The slide is going to tell you, okay, this is what's going to happen this time. What changed? Yeah? Yeah. Yep, exactly. So that's what we do all the time, right? We try to build up an hypothesis of what is this code doing, how does it work, what's going to happen with change, and we confront that to real data, factual data. What actually happened when I run it, or what happened when I do a trace, etc. So here, 1, 2, 3, 4, 5, 6 iteration. Okay. So there is one more iteration that went on here, because I switch from lesser to lesser equal. Does that make sense? Yeah. Lesser means I'm going to stop as soon as I reach 5. Lesser equal means I reach 5. I'm going to go one more time, and then I'm going to be at 6. I'm going to stop. So the end value after the loop is also 6. So we can start reasoning. Okay, we can use traces to see what the code is doing, and we can then look back at the code and start making hypotheses about how do those counter control loops tick? What makes them tick? What makes them work, right? What are the rules of the game here? All right. So this is me taking notes on the side and saying, okay, so when I use lesser equal, it looks like the number of iteration would be n minus start plus 1. And after the loop, n will be whatever n value I have plus 1. And I'm going to keep going through this. This is what I mean when I tell you, you guys are going to learn programming by tinkering. This is tinkering. Okay, this is me experimenting, changing things, trying to guess what's going to happen, looking at what actually happens, and trying to reconcile my view of the world with the computer's view of the world. And yeah, the computer is always right in that case, so I have to bend, okay? I have to adapt to whatever the computer is doing. That's my goal. I want to understand how the computer works. So I can troubleshoot it, so I can operate it, give it instruction reliably, etc. So I'm going to keep doing that. This time I changed the start value. Early on, I said, the start and end value, I should be able to plug in numbers. Those rules are not going to be affected by that. True. So far, it looks like it's true. So let's put it to the test. When you think something is true, try to find a way to disprove it. Do your best to find a way to disprove it. If you fail, your confidence that the thing is true should increase. Okay. If you find a counterexample, then that's it. It's false. All right. So number of iteration, n minus start plus 1, check. Still true. After the loop, n is going to be n plus 1, n value plus 1, check. That's true. So just changing the value, start value from 0 to 1, I just plugged into the same formula that I had. My formulas still hold true. They still allow me to accurately predict the number of iteration and the value of n after the loop. And then I'm going to get crazy. I'm going to speed up. So instead of incrementing by 1, I increment by 2. And I keep lesser and equal, and I keep starting at 1, stopping at 5, okay? So again, pause. Try to figure out what's going to happen. Try to come up with those rules. Then trace, see what actually happens, reconciliate the two. When you run this, it's going to do 1, 3, 5. Well, yeah, that makes sense because I'm incrementing by 2 every time, right? But hold on, it's not the main thing. The main thing is how many iterations. 1, 2, 3. So I come up with this formula, n minus start divided by 2 plus 1. And I'm going to keep tinkering and experimenting to make sure it holds true, right? But right now, this formula on that one case, on that one data point, the formula is true. But I need to look better, right? After the loop, it's going to be n plus 2. Where is that plus 2 coming from? So whatever I use as an increment here, if I use lesser equal, if I start at 1, 5, etc., it's going to be 5 plus the value of the increment because I do one more iteration. I hit the 5, and this is lesser equal, so that's okay. I go one more iteration, so I do plus 2. So whatever was the last value plus 2, 7, that's going to be it, okay? What else can we change? That one is funny. So I go back to speed 1 instead of speed 2. Start at 1, end at 5, but this time I don't do lesser than, greater than, lesser, equal, greater, equal. I don't use those comparison operator. I use different. While n is not 5, keep going. Should that change? A lot. No. I'm still looking out for 5, right? I'm still on the lookout for the value 5. I still increment by 1 every time, blah, blah, blah. No problem. I'm going to do 1, 2, 3, 4. So 4 iteration, n minus start. After the loop, n is 5. So this suggests that, testing lesser equal or lesser or different, well, 2 of those have to be maybe equivalent. Maybe. What about this one here? So I still use different, but now I speed up. Is that going to make a difference? Is that going to change anything? you had to take a guess on that one, what would you say? Number of iteration, and then value of n after the loop. Two iterations, okay. Everybody okay with that? I'm not validating, I'm just saying, okay, we have a proposal here, two iteration, going once, going twice, going thrice, right? All right, and then what about the value of n after the loop? 5? Okay, all right. Did you guys notice something? No, I mean, I'm not sure because some of you were using the font, but that might not be, related to doing trace table. I would understand that. But nobody took a piece of paper or started doing a trace table for that. Why? It's boring. It takes too long, right? Okay. So yeah, this little piece of code has only, like one variable. Yeah, we can do it by hand. Okay. So I don't blame you, but just, you see what's happening? Okay. Nobody wants to do trace, right? All right. So n minus start divided by 2 after the loop n is n, so 2 iteration, 5, perfect. Okay, you got it. All right. So, okay, what's going on here? So now I'm getting different formulas, etc. I'm a little confused. Okay, it's kind of going in every direction. So I need more data. So I'm going to take this one. And again, take a look at this one. Okay. Focus on trying to anticipate the number of iteration and then the value of n after the loop. What do you think? Yeah. Does it ever end? Well, actually, it's going to end in about 15 minutes, the class, but okay. No, does it ever end? That's a good question, right? Both for the class and then. Take a minute, okay? Like run it a little bit through your head. That thing is indeed going to never end. This is an infinite loop. So what's going on? I didn't do anything wonky. Yeah. It's never going to get equal to 5. But hold on a minute. I start at 0. I'm supposed to stop at 5. And I increment. If I start at 0 and I increment, I'm going to get to 5 eventually, right? No, right? I'm not going to get to 5 exactly. If I did lesser or equal here, that would be okay. But because I changed lesser or equal to different, my condition is not, reach 5 or above. My condition is you are going to stop when you reach 5 exactly. And if we run this, it starts at 0, then it goes to 2, 4, 6. So I get the idea, right? It's going to increment by 2 starting at 0. Okay, counter control loop. That's the part that's interesting. If I was tracing that on paper, okay, if I try to over focus on being a good robot, I'm going to trace and I'm going to go 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. And then I'm like, I'm running out of paper. Okay. What's happening here? That's why when you trace, you have to constantly think about what's happening, right? Because that's what's going to allow you to catch. Maybe you're going to catch it here. You're going to say, I go from 4 to 6. I miss my chance to stop. That was equal to 5 or different than 5. Now, I cannot possibly ever reach back 5 by incrementing by 2. That's it. You got it. Or you are going to trace and go 0, 2, 4, 6, 8, 10, 12, 14, 16. And by now, you're like really bored. And you're like asking yourself, is that ever going to stop? Whichever way triggers you to actually, do the robot dance, and then at the same time use your critical thinking ability to try to understand what's happening, and you will get to the point where you come to the conclusion that this is your problem here. That's a little bit more than tracing, what I just did. This is debugging. We're going to talk about it next module, right? But that's how important tracing is. When I want to understand code, I need to trace. When code doesn't behave the way that I want, and I need to figure out why, I need to trace. Yes. How do you stop an infinite loop? You don't. In JGrass, there is an end button as a console at the bottom, so you don't have to throw away your computer, and burn it. You can still reuse it for other stuff. But yeah, that's a good question, right? When you run a Java program, if it's at the command line, Control C. If it's in JGrass, there's an end button in the console. If it's a graphic user interface that you're running, written in Java, and it's doing something like that, Task Manager. Go and shut it down with a shotgun from there, okay? So that's it. So that kind of like gets us a little started in, well, okay, we can use that for understanding code. We can use that to predict code. We can use that to find flaws in code. And then I told you at the beginning, when you are in an exam, the trace table bit, like the Excel document, etc., it's not going to fly. That's not going to fly. Why? One, it's slow. But that's okay. If you do something slowly long enough, you get faster. Okay, that's just us. That's how we learn, to get faster, right? But the more important thing is not that it's slow. It's a very, how to say, fileable, I hope this is a word, fileable process, a process that can fail very easily, okay? Again, human nature. If you ask me to trace, it depends on how awake I am, how upset about something, or worried about something, or maybe I'm tracing in front of 300 students in an amphitheater, and there's my chair there, and the dean, etc. And I'm like, wow, if I mess up a trace for that program, they're all going to think I'm a moron. Okay, that kind of stuff can really mess with you, right? Everybody can walk on a plank of wood that is this wide. We can all walk on it if it's on the floor. If it's between two buildings, I have reservations. Okay, so that kind of stuff can mess with you. Bottom line, we need something more reliable. So there are two ways. The first one, historically, this is what every computing student has done at some point in their life, since I can remember, right? It's called instrumenting the code. Instrumenting the code means this is my code and this is new. What the hell is this? This is a system.out.println that has been added at the end, right before the end of every loop. And it displays n equals the value of n, and the result equals the value of result. So yeah, this is a point in the course where I get sick and tired of writing system.out.print n equal, then system.out.print the value of n, then system.out.print result equal, and then system equal.println the value of result. Those four instructions, I can do it inside one println. There's just a little bit of syntax for you to know, is you can use a plus, not in the sense of addition in Java, but in the sense of put those string of text together. So here's the text I want you to display, plus concatenate at the end of the text, add to the end of the text, the value of this thing, plus put some more text, plus the value of this thing. So that's how you can display more than one thing in a line without going nuts and having four statements like I've been doing until now. And you can have, like, for example, here, pretty much a trace done for you. Okay, that's the goal. If I run this, look at what it's going to do. Very soon it's going to do something, I promise you. There we go. It's going to run, and we call it instrumenting. That means that we added some operation in the code that produce a log file or maybe just an output on the console that tells us iteration by iteration, these are the value of n and result when we reach right before the end of the loop. And that helps me figure out what's happening. Okay? It's like making your trace. So when you do your trace by hand, like when you download the code, play with it, etc., you can run the code to validate your trace. But what if you get it wrong? What if your trace is wrong? It might be interesting to know exactly what you did wrong. That's how you're going to learn and get better, right? So this will help you actually realize what you did wrong. And then the last one, we're just going to finish real quick with this. I'm going to fire up JGrass, good old JGrass. This is a code that you can download from Canvas. So this is the code we have been using in the slide. Let me make sure that it still compiles. Compiles okay, runs okay. All right, so right now, no instrumentation, no extra printf. It just does exactly what I showed in the slides, right? So there is a tool in JGrasp called the Debugger that we are going to use obviously for debugging. So that's going to be next module. But for this module, it's going to help us also make traces very reliably. So I just want to show you how that thing works. It's the very basics of the debugger. And then if we need more features, we'll add them, okay? But let me show you the most basic way to use the debugger in 2 minutes. You have your main method. This is the first thing that happens in the main method. I'm going to put my mouse past the line number. By the way, the line numbers, you can add them and remove them. Where is it? Is it here? Yeah, like this, okay. Past the line number, there is a little gray margin here. Tiny little gray margin. Put your mouse exactly on that gray margin. And I do realize you don't see my cursor, so that doesn't help. So I put my cursor here. And when I do it on my JGrasp, there's a stop sign that shows a big red stop sign where my mouse is. And I click on it, and it puts what is called a breakpoint. A breakpoint is it's a stop sign. It's a way to tell JGrasp, next time I run this code, when you reach this line, I want you to stop. Stop execution, freeze everything. And that's where the debugger is going to allow us to start a program, stop it right at the beginning, and then very carefully execute step by step the code, one line at a time, and keep an eye on the values of the variables in memory. How do we do that? Well, you compile your code, and instead of running it, the running man icon here, you're going to use the beetle icon next to it. That one, okay? So you click that. I don't remember the keyboard shortcut for it, sorry. But you click that, it's going to look like it's starting to execute your code, and there is an arrow here that's going to say, this is where I am. The arrow tells you I am about to execute line 6, but there is a stop sign, so everything is paused. Look, the code is not doing anything here. It's just waiting, like if it was waiting for input, right? But there's no scanner. It's just waiting to continue execution. And now this panel here changed a little bit. This panel on the side here is now our debugger panel. So we were usually in the browse panel, okay, to load up files and stuff like that. When you turn on the debugger, you get into the debugging panel. It has 2 parts. The top part, I'll talk more about it in a few sessions. So for now, we can safely ignore it. But the bottom part, that's the juicy stuff for us right now. This is telling us we are in the main. So this is also what's telling us here, right? It's telling us you are in the main method, okay? And this is what I have. I have some arguments. So these are the parameters of my method here, args. We don't care about that. We have local variable. No, we don't have any local variable. I didn't declare any variable in my main. So I'm going to now say execute the next step. And this is how I do it. You see those 2 arrows here, the one that goes down and the one that is bent, okay? That means execute everything on the line, but don't show me the details. Go through, okay? And that means execute everything on the line where you are at, but if you call a method, I want you to go inside that method and show me what's happening. So let's try both of them. I'm going to try the straight arrow first. Boom. It executed line 6. It executed the whole loop method, call that method, and then I'm done. And if I try to go again forward, I'm out of the debugger, execution is complete, okay? So every time you execute like that, everything is going to happen like it should on the screen, but you don't see the details, right? So let me try to run it again. Click the debugger. I'm on line 6. Now I'm clicking the bent arrow. This one. Now it's saying, okay, I'm going to remember that the method was called here. So there's a gray arrow, like a bookmark. And then it says the next line that gets executed is line 10. And now it's going to show me here what happens in the method as I run line per line. So I'm going back to the straight arrow because I don't want detail. There's no method being called anyway. And I'm going to click. Start value is 0. End value is 5. N is 0. Let me make that a little smaller so that you can see. There we go. And I keep clicking on that straight down arrow. and it's going to display loop from n equal the start value. So all of this is happening in the console down there. Okay, display this, and then set the value of n to start value. There we go. Oh, wait, did I miss the button? Yes, I did miss the button. Sorry about that. Okay, when you execute that, n is assigned the value here 0. While n is lesser than value, it's going to compute. This is true, so I go to line 22. I'm doing my trace step by step. And when you modify a variable, when you just change its value, okay, it's going to show you in red, this value just got changed. So watch out. So it does exactly what my trace table is doing. It does it automatically for me. Again, why do I annoy you with the trace table? Because I can watch the debugger go through, and yep, I understand what's going on. Yep, but I'm not doing it. I'm not creating the connection in my brain that allow me to predict efficiently what the code does. Okay, it's like saying, I'm not going to train for that, whatever martial art tournament in 2 months. You know what I'm going to do? I'm going to watch YouTube videos. That's exactly what I need. And everything is going to be okay, right? So exactly the same thing. I can watch the debugger. It's not going to help me develop the skill, but the debugger will help you make sure your trace are okay, figure out where your trace fell, get better, and in exam, yeah, you'll definitely use the debugger. All right. Thank you, everyone. Just one second.